In this video, I'm going to continue on our discussion of reactions of alkenes. And so in this one, I'll be talking about halogenation and the production of halohydrins, hydrogenation, lots of H words here, and addition of carbenes. All right, so we'll first start with the addition of halogens to alkenes, which has the general scheme of this where we have our alkene, we have our halogen, and this then forms usually with an anti-addition, and we'll see why here in just a second, why that's the case. So we start with something like our propene here, which is, I guess this should actually be one propene, so one propene. But anyway, we have our alkene here, and then we have our halogen right here. And so we are going to have the electrons from this come out and grab onto this right here. This is going to go over there, and then this one is going to bond onto that carbon right there. So we end up with this bromonium ion right here. We can then take this down here where we can bring in another bromide right here. It could be the same one, it doesn't really matter. And this is going to attack the carbon that has the most partial positive, which is going to be the most substituted one. So we have partial positive on both of these carbons, but this one is more substituted right here. And so we're going to bring this in onto that carbon. The electrons go up onto the bromine there, and so we end up with this. So the 1,2 dibromopropane right here. And we see why this is the anti-addition right here, because when we have this bromonium ion up here, this bromine or this bromide ion right here is going to attack from the bottom so that we can get this sort of SN2 reaction going on here. And so that's going to attack from the other side of the carbon that the positively charged bromine is bound to. And so that's why we get the anti-addition there. And so chlorine and bromine can commonly be added to alkenes by this halonium ion. So whether that is the bromonium or the chloronium ions. And so those can be commonly added with this mechanism. So iodination is used less frequently because the diiodides decompose easily. So when we get to something that looks like this but with iodines on it, those can decompose fairly quickly. So any solvents used have to be inert to halogens, so we can't have something that the halogens will react with. And things that are good for that would be things like methylene chloride, chloroform, and carbon tetrachloride. So yeah, because of that anti-addition, what we see is if we have something that looks like this, where it's like a rigid bond here so that it's held in place, so we can't just swivel around that newly formed single bond. So something like a cyclopentene, we're going to end up with the trans version of it here, because one of the bromines will get added to either the top or the bottom, and then the other one will get added from the opposite direction of that one that added first. And so if we have something like this where we can't turn around this bond right here, then we will end up with the trans conformation here, or the trans stereoisomer rather. All right, so formation of halohydrins. So we're going to do essentially the same thing we did before, and in this one we're just using chlorine rather than bromine for no apparent reason. So those are going to be the two things, chlorine and bromine, that are commonly used in these reactions. So again, we're going to have the electrons go here. These electrons will go onto there. This lone pair will come and bond onto that carbon. So we end up with our chloronium ion. So we can then go down here, and so now instead of having a chlorine come and attack this more substituted carbon, we'll have water come and do that. So this will come attack that carbon. These electrons will go onto that chlorine right there, and so we end up with this. We could then have this water come and take a hydrogen from here. The electrons go to the oxygen, so we end up with a hydronium ion, and now we have this chlorohydrin here. So it has this chlorine on it, and it has this alcohol group right here. So that is a chlorohydrin. So for this, we can do the chlorohydrin, we can do the bromohydrin, and we can, in fact, do the iodohydrin here. So we could do this with all three of those. And again, for this, we're going to end up with the anti-addition, but we'll also end up with both enantiomers here if we have something that that looks like this. So we can end up with the RR enantiomers like we have right here, or the SS enantiomers right here, but they're both going to be trans. So it will be the trans stereoisomer for each of them, but we will get a racemic mixture of the two enantiomers for this. And again, we can see that we also get it so that the water is adding to the more substituted carbon on here. And that is because when we are at this place here, this water will bind to the one that has the stronger partial positive, which will be on the more stable carbon, or the carbon that can carry that partial positive better. All right, now switching gears a little bit, we're getting to catalytic hydrogenation. So you may have heard of, things like partially hydrogenated vegetable oil. So when they say hydrogenated, what they mean is they're taking something like an unsaturated fat, which would have double bonds in the hydrocarbon chain of it, and then they're adding hydrogen here so that they get a saturated hydrocarbon here. So when they do that to, something like a vegetable oil, they can, make it look sort of like butter, because vegetable oil is liquid because it has those double bonds in it. It has those unsaturated fatty acids in it, and then when they hydrogenate it, they can get it turned into the saturated fatty acid, which is going to have a higher melting point, and so it becomes more of a solid, so they can make like the fake butter from it. But anyway, we'll be looking here at the catalytic hydrogenation. So for this, we're going to use one of these catalysts here, the platinum, palladium, or nickel. And so we'll have our alkene and our hydrogen gas here. And so we will be adding those hydrogens across that double bond here. And so for most alkenes, hydrogenation takes place at room temperature. A small amount of platinum, palladium, or nickel catalyst is added in the container. And then the container is shaken or stirred. So the hydrogenation takes place on the surface of the metal. So the hydrogen gas is adsorbed onto the surface of the metal, onto the metal catalyst, and the catalyst weakens that bond between the two hydrogens. So when the hydrogen, so for instance, when hydrogen and deuterium are mixed in the presence of platinum, the two isotopes quickly scramble. So if we have our hydrogen and our deuterium here, which is just an isotope of hydrogen, and we mix it with platinum, these things will scramble so that we end up with some H2, some D2, and some HD molecules in there, because that platinum is breaking those hydrogen bonds, which is what we want for hydrogenation. So we have here this that I have in gray is our platinum catalyst here. We bring in our hydrogen gas, and so the bond from this, so we're going to have one electron go here and one go here, so that our hydrogens end up bound to that platinum. So they're adsorbed onto the surface of the platinum. Then we can bring in our alkene, which here we're looking at just a cyclopentene here. So we're bringing this in. So we have our catalyst with the hydrogen adsorbed. This is going to come down and adsorb onto the platinum as well. So this double bond here will adsorb onto the platinum as well. Those electrons will be attracted to this platinum here. So then we have the catalyst with hydrogen and alkene adsorbed onto it. So then one of the hydrogens will insert onto the carbon-carbon double bond on our alkene like this, and the alkene will then be bound to our platinum like this. Then the other hydrogen will bind onto the other carbon here. So this other hydrogen will then go to that carbon there. And so then we will end up with the alkane product releasing from the catalyst like that. And I'm not going to go into too much detail of the sort of organometallic mechanisms here. That will be something for future videos, probably in my inorganic playlist. But for now, we can just use this as our sort of mechanism here for the hydrogenation of this alkene. All right, and so we can also use what's called Wilkinson's catalyst, which is just a rhodium or ruthenium phosphine. So we have this right here. If we want the 3D structure of it, it looks like this here. So those pH3s are those phenyl groups, so those benzene rings bound onto the phosphorus, which is then going to complex with our rhodium or ruthenium our rhodium or ruthenium metal right here. And so we can actually use this to do this hydrogenation as well. And so, I mean, this might seem like kind of an interesting curiosity, but what becomes more interesting is when we can substitute different chiral ligands for the triphenylphosphine. So we have these big triphenylphosphines here. We can actually put chiral ligands onto them, and we can actually use that to convert an optically inactive starting material to an optically active product. So we can actually we can have this be enantioselective here. We can actually select for the R or S enantiomer in our product. And so that's why this process is called asymmetric induction or enantioselective synthesis. So we could use these molecules here as our ligands onto this rhodium or ruthenium metal. So we have this rhodium or ruthenium metal right here, and we can actually put, instead of just these triphenyl phosphines, we can put things that look like this onto it. So this is our phosphorus right here, and we can have either an R or S chiral molecule as the ligand onto it. And so we can use something that looks like this. So this RU binap Cl2. So the binap standing for this 2,2' bis diphenyl phosphino 1,1' binaphthyl right here. And so we see we have this metal right here with our two chlorines. That's the Cl2, and then the binap, which are these larger groups going on here. And so we can, for instance, take something that looks like this, which is optically inactive. It does not have, it's not chiral, so it doesn't have any enantiomers. And we can use one of the enantiomers for this up here. So we could use this R1 up here. And so we could then create 96% of the R version right here. So we can, I mean, you could use the S version up here as well to get the S version of our product. But the point is we can use a catalyst that has a certain chirality and then form a product that has that same chirality, or at least has a more pure chirality, which is, you know, actually, I mean, this might seem like just another sort of, you know, gee whiz curiosity, but this is actually extremely important for, you know, things like pharmaceuticals and stuff like that. In fact, I think, you know, some of this stuff like this, I think won Nobel Prizes. I think people won Nobel Prizes for coming up with these kinds of things, because being able to make these pure enantiomer solutions or products rather is extremely important in a lot of our sort of everyday things, where pharmaceuticals is probably sort of the standout place where that's going to be important. And so, you know, this isn't just like some, sort of isn't that interesting kind of thing. It's also, has a lot of practical uses for it. All right, so next I'm going to talk about the addition of carbenes to alcohols. And so remember, a carbene is something that is a carbon. It can have hydrogens or R groups on there. Then it has a lone pair on it. And we can see that this species here does not have a full octet on the carbon, and so it's actually extremely unstable. And so we get this mechanism right here where the electrons are going to bond to one of the carbons. The electrons from the double bond then go to the carbon on the carbene, and we end up with this cyclopropane species right here. So this is using methylene, which is just a carbon like this with these two hydrogens bound to it. And so it's a very strong electrophile because of the incomplete octet. And so the electrons from the double bond here are going to bond very quickly with the carbon on the carbene here. And so one way we can make a carbene is from this diazomethane, but this is extremely toxic and it's explosive. So what we're doing is we're taking heat and UV light onto our diazomethane here, and we're going to produce N2 and methylene here. And so one of the issues here, because it's, not just because it's toxic and explosive, but these carbenes are also just extremely reactive. And so when we use some light here on our diazomethane and we have our alkene here, we're going to get a bunch of these side products. So we're not just going to get this propanated hydrocarbon right here. We're also going to have this carbene add onto these other carbons. So we can get it adding right here. We could get it adding right here or right here. And so we can get a bunch of different side products from this that we don't actually want. And so we need to come up with some other way of adding these cyclopropanations on here. And so one of those ways is what's called the Simmons-Smith reaction. So we use methylene iodide plus this right here, which is just zinc dust with some copper impurities in it, and we get the Simmons-Smith reagent, which is called a carbenoid. And so what we mean by that is that a carbenoid reacts much like a carbene, but does not actually contain that divalent carbon atom. And so we get a reaction that looks like this. So we bring in our alkene, we have our Simmons-Smith reagent here, then we form our cyclopropane product right here, and we give off this zinc iodide right here. So if we look a little closer at this mechanism, so we have the zinc plus this right here, which has a carbon in between these two iodines. We end up getting this zinc kind of put in the middle here. And so then we bring in our alkene. We get a transition state that looks like this, where we see this carbon right here is the carbon that was in the middle of our Simmons-Smith reagent right there. And so that's going to bond onto this double bond right here. Then this zinc with the two iodines here is going to leave from here. And so we end up with our cyclopropanation going on that alkene. So one other way we can do it is we can do it by what's called alpha elimination. And so we have this bromoform here, which is just a carbon with 3 bromines and a hydrogen bound to it. We put it in our hydroxide here. This will come grab that hydrogen there. The electrons will go to the carbon. So we have this carboanion here. And then because that's so unstable, one of these bromines is going to leave from it. So it's going to leave like that, and we end up with our dibromocarbene right here. And so if we react that with an alkene like this cyclopentene here, so we have our bromoform that we can see up here on the top, and then our hydroxide, our potassium hydroxide right there that will be taking off that hydrogen. So we end up with a cyclopropanation going on here with these two bromines coming off of it right there. And so this will conserve the stereochemistry of the alkene here. So if we have a trans alkene here and we add this, if we do this cyclopropanation, we will maintain the trans stereochemistry on the carbons there. And same if we have the cis right here, we have the cis, and this is the trans. When we add that on here, we will maintain the cis stereochemistry on those carbons back there. But anyway, that was what I wanted to talk about in this video. Again, just to sum up, we did the addition of the halogens to alkenes, and so we had the anti-addition here because we are forming this this halonium ion. In this case, is the bromonium ion. Then the other bromide is going to attack from the bottom and SN2 reaction, and so we end up with this right here. And so if we're doing this on something that's rigid, where we can't just rotate around that single bond, so such as a cyclopentene, then we will get the trans isomer for this here. Then we also looked at the formation of halohydrins, which had a similar mechanism, but now instead of bringing in a halogen here, we're bringing in a water so that we end up with an alcohol and a halogen bound to our hydrocarbon there. And again, if we bring in something that isn't able to just sort of freely rotate around the single bond, we get the trans isomer, and we will get in a racemic mixture of both of the enantiomers there. Then we looked at the catalytic hydrogenation, which is just adding hydrogen across the double bond so that we turn an unsaturated alkene into a saturated alkane. So we do that using this platinum catalyst, or we can use palladium or nickel, but I think platinum and palladium are actually the two most common ones. But we can also do this with the Wilkinson's catalyst, which was interesting because this allows us to have the enantioselective synthesis here. So we can actually, using the different enantiomers of our catalyst, we can actually select for one of the enantiomers in our product. Then we also looked at the addition of carbenes to alkenes. So the carbene being something like this methylene right here. But we want to have something that's a little bit less reactive, so we're not getting too many of these side products. So we could use something like the Simmons-Smith reaction that uses the Simmons-Smith reagent that is this carbenoid here. So we can get our cyclopropanation from that. And we can also do it from the alpha elimination on something like bromoform here, so that we get our cyclopropanation like this with the two bromines coming off of it. And that will conserve the stereochemistry that we had on our alkene. But anyway, I hope you found this video helpful, and I will see you in the next one.